Okay, with no further ado, welcome everyone to this introduction lecture on density functional theory, in which we cover the basics of DFT. And in today's lecture we will cover 5 different topics. The first one is the material modeling scheme that will us provide an overview over the different modeling schemes and where we can apply DFT. That will provide us with a better understanding what DFT can actually do and what DFT can't do. So to get a better understanding and feeling in which research questions we can actually apply DFT and where we can't apply DFT. Then the second part of the lecture is the fundamental equation of quantum mechanics, the Schrödinger equation, and together with the associated Born-Oppenheimer approximation. The Schrödinger equation, as I said, builds the foundation of quantum mechanics. It explains why we get the quantized values of our energy, for example, and then the Born-Oppenheimer approximation provides us with a practical implementation to solve the Schrödinger equation, because solving the Schrödinger equation in material science and physics and chemistry becomes quite a challenge for systems with more than one electron. So we can actually solve it, as we discuss later, for hydrogen, but then it becomes problematic if we go beyond hydrogen. The third part is the electronic density. In this part we will understand where the electron density comes from, what does it mean, and what does it mean for density functional theory, because as the name implies, it's based on the electronic density. And then in the last 2 topics we will actually cover the basics of DFT. So first we will cover the Hohenberg-Kohn theorems, which laid the foundation for DFT. And then last but not least we will cover the Kohn-Sham formalism. Sometimes it's also called, in modern times it's called the Kohn-Sham DFT, because it's the current implementation, how we actually use DFT. So to make a distinction between Kohn-Sham, between Hohenberg-Kohn and then later Kohn-Sham, sometimes Hohenberg-Kohn, the implementation of Hohenberg-Kohn is called Hohenberg-Kohn DFT, and then the modern version for Kohn-Sham as a Kohn-Sham DFT. Okay, with no further ado, let's move towards the modeling scheme to understand where we can use DFT. So in physics, chemistry, engineering and material science, we model various properties over various length scales and time scales. And we're interested in various questions. We're interested in electronic structure properties or atomistic structures. Those are taking place in a quite narrow, in a quite small range, right, in picometer and attometer, angstroms, and in the nanometer regime. But we might also be interested, especially if we go towards larger systems and simulating and modeling whole devices, and then we are more into this mesoscopic and macroscopic regime. It's quite important to understand that each single different regime, the electronic and the atomistic, which we cover in this topic, but also then later the mesoscopic and macroscopic, which we're not covering that in this lecture, they need their own modeling solutions and methods. There's currently no method which covers the whole length range. We currently don't have a method which is capable to simulate electronic structures, for example, of a molecule, and then in the same time also simulate the whole device, like a battery or a solar cell. So give us a better understanding which methods are available, especially for the electronic and the atomistic regimes, which we cover in that course, we will focus on those now. So the first thing is we have ab initio methods, sometimes also called wave function methods. Those are there to simulate electronic properties, and they take quantum effects completely into account. So their modeling takes place entirely in the quantum regime. If we go one step further, we end up with density functional theory, which we will discuss today, and it also takes place in the quantum regime, but also goes beyond that, and it covers electronic properties as well as atomistic properties. And going one step further, we end up with methods like tight binding or force field, you might have heard of, and also nowadays machine learning interatomic potentials, where a machine learning interatomic potential is similar to a force field. And in this course we will basically cover DFT and the machine learning interatomic potential. So DFT will be covered in the first 2 lectures and then the first 3 tutorials, and then MLPs in the 2 last lectures of that part 2 and in the last tutorial. And it's quite important to understand the link here. So with DFT we can model a couple of 100, I would say up to 1,000 atoms to obtain electronic properties, whatever, like the band gap, optical properties, bulk modules, stuff like that. And then if we want to go to larger systems, we could use tight binding or force fields. Or nowadays we use the machine learning interatomic potentials, which are trained, for example, on DFT data. So they aim for a DFT type accuracy, but with not the cost of DFT, and that allows us actually to simulate and model a couple of 1,000 atoms. So we can push towards a mesoscopic range with the MLPs, providing us still with quite a good accuracy. So DFT is more like for that regime where we have a couple of 100 atoms, and if you want to go beyond that, then you need to choose another method. So DFT can't do infinite systems with an infinite number of atoms, and that basically sets the boundaries for DFT what to model in the length scale. Right? If we have a unit cell, it can do a couple of tens angstroms, but then it reaches its limit. Okay, with that we had understood where, in which regime DFT works, and also where machine learning interatomic potential works. And the next step is to go to the Schrödinger equation and the Born-Oppenheimer approximation, which will be discussed in a second.